Now let us come back to Hilbert's conjecture about the existence of Hilbert Class Field. Given a number field k, previously we have constructed an extension k tilde of k satisfying 1 and 3. In other words, we have constructed a Galois extension k tilde of k such that the Galois group of k tilde over k is isomorphic to the ideal class group of k. Any such extension k tilde will have the property that for all k prime p, the order of p in the ideal class group of k is just gonna be equal to the inertia degree of p in k tilde over k. In particular, p splits completely in k tilde, i.e. this inertia degree is 1, if and only if p is principal in OK. So let us quickly review how we constructed this extension k tilde. This is actually a consequence of Takagi's theorem. Recall that Takagi's theorem gives us a correspondence between ideal group and finite abelian extension of k. For every ideal group H of k, its corresponding class field, it's gonna be a finite abelian extension of k whose Galois group is equal to the generalized ideal class group corresponding to H. Now, coming back, if we take the modulus m to be 1 and H to just be the group of principal fractional ideal, then in that case, the generalized ideal class group corresponding to H is just the ideal class group of OK. And so, by Takagi's theorem, the corresponding class field, the class field of H, is gonna have Galois group over K being isomorphic to the ideal class group of OK. Furthermore, by Takagi's decomposition theorem, we know that if L is a class field of the ideal group H with modulus m, then for every prime of OK not dividing m, we have that the inertia degree of the prime p in L over k must be equal to the order of p in the generalized ideal class group corresponding to H. This in particular implies part 3 of Hilbert's conjecture. Because recall that in this case, k tilde is the class field corresponding to P1, and the generalized ideal class group corresponding to H equals to P1 is just the ideal class group. And now we're ready to prove number 2, i.e. we want to prove that k tilde as constructed is going to be the maximal unramified abelian extension of k. This is usually used as a definition of the Hilbert class field of k. Okay, so let us start with an abelian unramified extension L over k. Recall that in the previous video, we have discussed the fact that the primes of k that ramify in L are exactly those that divide the conductor of L over k. Therefore, for L over k to be unramified, we must have that its conductor is trivial. But now recall that the conductor of L over k was defined to be the smallest modulus m such that L is contained inside the ray class field corresponding to the modulus m. Therefore, we must have that L is contained inside K1, and thus its corresponding ideal group must have modulus 1. But now recall that our correspondence between class fields and ideal group is inclusion reversing. That is, if two ideal group H1, H2 of the same modulus are such that H1 is contained inside H2, then L1 must contain L2. In our particular case, since the ideal group of L contains P1, we must have that L is contained inside the class field of P1, which is just, by definition, K tilde. So, K tilde contains all unramified abelian extension of K, and thus it's the maximal unramified abelian extension of K.